video is on probability experiments, and one really important thing to take away from probability experiments is the more times you do them, the more accurate it becomes. So just do it over and over again, basically. So, nice to know you, let's do it again. A lot. Okay, now we need to introduce this idea of relative frequency. So it's similar to frequency, but it's relative frequency. And it has an equation, of course, because this is maths. So the relative frequency is the frequency divided by the number of times you did the experiment. So it's not too bad, but it's made so much easier when we think of it in context. So let's have a go at that. So I'm going to roll a dice 100 times. And then I'm going to count how many times I get each number and record it in this table. Okay, so I threw this dice 100 times and I got 1, I rolled a 1, 20 times, a 2, 12 times, I rolled a 3, 18 times, etc. So that is the frequency, the number of times I roll it. So now we want to calculate the relative frequency for all of them by using this formula. So I'm going to add a row to my table called RF for relative frequency. And basically I do the frequency over the number of times I did the experiment, and I rolled it 100 times, so that's going to be 100. So I did frequency, so it's going to be 20 divided by 100, and that is a fifth. It's going to be 12, the frequency, over the number of times I did it, 100. So 12 divided by 100 is simplified down to 3 out of 25. Here I'm going to have 18 divided by 100, which is 9 out of 50. So now we've calculated the relative frequencies. And if I roll this 1,000,000 times, I'm going to get closer and closer to the actual true probability. So as we know from a fair dice, it should be a 1 in 6 chance of rolling a 6, a 1 in 6 chance of rolling a 5. They should all have probability 1 out of 6 of me rolling the number. And the more I repeat this experiment, so the more times I do it, the more accurate. So if I repeated it like infinite amount of time, like as many times as I can, the closer and closer I'm going to get to getting these values to be a sixth. We also need to ask ourselves if things are fair or biased. So unfair, that means. So when I'm doing a probability experiment, I want it to be a fair experiment. So if I'm rolling a dice, I want it to be, and this is why they always seem to use the notation, a fair six-sided dice. So I have an equal probability, a fair chance of landing on either of these. So in an exam, you might be asked, do you think this data is biased? So is it fair or not? So what you want to look out for there is any outliers, any extreme values. So if I did the experiment I just did, and I rolled a number 1 50 times, so half the time I was getting a number 1, that would kind of say, oh, maybe our dice isn't fair, that seems to be biased. They probably put like a weight or something on the 1 to always roll a 1. Sometimes you have two-step experiments, and in that situation I recommend that you draw a tree. It's a bit like a prime factor tree or a probability tree. So my experiment is going to be about if you set an alarm or if you didn't set out an alarm, and then the next question is going to be, did you get out of bed on time? Did you not get out of bed on time? So the way this works is that we have two steps. Step 1 is the question, did they set an alarm for 9 AM? And then step 2 is about the probability, did they get out of bed by 9:30 AM? So it can kind of depend on, if you set an alarm or not. So the way this works is like this. Let's say we have 100 people in our experiment. We start with 100. Then we ask them this first question. And the answer is either a yes or a no. So let's say we have 64 people setting their alarm for 9 AM. You would have 64 of your 100 there. And then obviously you need to make 100 up here. So you've got 36 saying no, they didn't set an alarm for 9 AM, and 64 saying yes, they did set an alarm for 9 AM. That is step 1. Now we move on to, did they get out of bed by 9:30? So again, you can either have yes or no for each of these answers. So let's say they set an alarm for 9 a.m. and they got out of bed by 9:30. Number of people that said yes was 30. Therefore, we now know the number of people that said no, it's not out of 100 anymore, it's out of 64, because we've only got, these are the ones that set an alarm. So we're going to have 34 that didn't. What about if we look at the yes for here and we say 6? These are the people who didn't set an alarm, and then we've got 6 of them, however, just got out of bed before 9:30 anyway. And then saying no, again, it's not out of 100 now, we're up to 36 that didn't set an alarm. So that is going to be 30 there. So that is how a tree works if you have a 2-step experiment. And now we can, the whole point is to work out relative frequencies. So if we do that, the way this happens is yes, followed by a yes. So if you go yes, then yes, you have, the end is 30. So that is 30, the frequency, out of the number of times you did the experiment, and that is the total number of people, 100. If we look at yes, then no. So you set an alarm, yes, and then you didn't get up before 9:30. So that is, frequency is 34, and then again it's out of the same, 100. What if we look at no and then no? What's the relative frequency of that? So no and no is 30. It's out of 100, so we can cancel these down. What about no and then yes? What's the relative frequency of that? No and then yes. That is 6 out of 100. So they can all be simplified down a bit, but that's how you'd use a tree, which can be really helpful to work out relative frequencies sometimes. So the next thing we're going to look at is the idea of expectation, so expecting something to happen. And this can happen, say you've done an experiment n times, so loads of times, you might be able to actually expect something to occur a certain amount of times because you've kind of got enough information. Expected frequency does have a formula, of course, because we love a formula. Expected frequency means like the expected number, basically. Frequency can, in a more Englishy term, would be just number. So let's go back to the classic dice. So the best way I'm going to explain this is an example. So I roll a dice 60 times. How many 6s do I get? So this is when you can use the idea of expectation. So how many 6s do you expect to get? So the expected frequency of 6s, basically. So that's going to be the probability of a 6 times the number of times you do the experiment. So the expected frequency of the 6, the number of times you'd expect to get a 6 after rolling a dice 60 times would be the probability of getting a 6, which on a fair 6-sided dice would be 1 out of 6, multiplied by the number of times you do the experiment, which here was we rolled it 60 times. So that means we're expecting to get 10 6s. So that's the expected frequency, the expected number of 6s if we roll a dice 60 times. So that's a really useful formula to remember there.